We're going to extend our discussion of weak acid dissociation with an example of a dilute solution of formic acid. This is the same equilibrium constant and the same chemistry that we talked about earlier, where we had an initial concentration of 0.534, except this time we're going to go a couple of decimals more dilute and go 0.00534 molar in formic acid. And just a refresher is that we have our Ka is equal to the concentration of H3O plus times the concentration of formate HCO2 minus divided by the concentration of formic acid HCO2H. Okay, and we are just going to copy from our existing ice table, the same table that we used earlier, with the exception that now we've changed our concentration to be 0.00534. And so we're just going to go ahead and fill out this Bx squared divided by 0.00534 minus x. Okay, so that is just basic getting us started again, and I'm going to now move to a separate screen, and we're going to move down one. Give me just a moment. All right, very good. Start back our annotation and are going to continue on. Again, we're going to do a rigorous quadratic calculation and compare that to the small x approximation, and just carrying forward from where we started on the last screen. I'm going to go ahead and put in the data, 1.8 times 10 to the minus fourth. Again, that's the Ka for this equilibrium reaction, and that is going to be equal to, again, x squared divided by 0.00534 minus x. Okay, and we will do a little bit of manipulation here to show that 0 is equal to x squared plus 1.8 times 10 to the minus fourth x minus 9.612 times 10 to the minus 7. Okay, so I skipped one step there to get us right to the quadratic, but you can do this yourself, and you would want to probably for just experience. So A, again, we're going to now use our solution for quadratic. A is equal to 1 here. B is equal to 1.8 times 10 to the minus fourth. And C is equal to minus 9.612 times 10 to the minus 7. All right, so let's carry that forward. So we have B is equal to 1.8 times 10 to the minus fourth again. B squared is therefore equal to 3.24 times 10 to the minus 8th. For AC is equal to minus 3.84 times 10 to the minus 6. And therefore, again, continuing to work through this calculation piece by piece, which is the way I like to do it. Otherwise, you might miss a decimal point or miss a number. So I break it down to more simplicity. B square root of b squared minus 480c. Again, that's under the square root, which is right here, right? That is equal to 1.97 times 10 to the minus 3. Okay? And now you can plug all of this back into our expression here and go to, and I'm again probably skipping a step here. Let me change that. So the concentration of H plus our hydronium ion is going to be equal to X. And when you plug in these pieces back into this quadratic expression for X and solve that, you get X is equal to 8.95 times 10 to the minus 4th. I'm going to put a semicolon here. Now that we have the hydronium ion concentration, we can calculate the pH. And that pH turns out to be 3.05. Okay. Now, that's moving. That is the calculation, the rigorous calculation for pH. Now let's use our small x approximation, where our Ka, again, is equal to 1.8 times 10 to the minus 4. And that is equal to x squared over 0.00534 minus x. But we are going to approximate here, so I'm going to put a big red mark out there for the x, since we're simplifying, right? We're making our small x approximation. Therefore, x squared is equal to 0.00534 times, let's do a times there, 1.8 times 10 to the minus 4th. I hope you can see that. All right. That equals x squared equals 9.612 times 10 to the minus 7th. The square root of that will give us x, which is equal to the hydrogen ion concentration, and that equals 9.8 times 10 to the minus 4, okay, which will give us a pH, again, the minus log of that number will give us a pH of 3.01. So with the small x approximation, we got a slightly smaller pH than we did with the rigorous quadratic expression for hydrogen ion concentration. That differs a little bit from the previous example where we had when our concentration of formic acid I'm just going to simplify that and say was equal to 0.534. Then pH for both cases was equal to pH, to 2.01. 2.01. So there is a difference here as we go more dilute in the concentration of the dissociating weak acid.